the first part of the lecture, we look into the membrane potential and describe it in terms of the equilibrium condition that is given by the Donnan equilibrium. The final conclusion will be that we cannot explain the membrane potential as an equilibrium. Hence, we need an active process which will be developed in Part B. Let's recap on Physics of Life 1, where we learned about the Nernst potential. The Nernst potential will develop in a situation where two compartments are separated and the internal and outer side ion concentration is different. If we now consider an equilibrium situation in which the concentrations of the outside and inside have to obey the Boltzmann distribution, we know that the ratio of the inside to the outside concentrations is given by e to the power minus z times E times delta V divided by kBt, where E is the charge of an electron, Z is the charge number of the ion, and delta V is the potential that will develop. Now, turning this equation around, we obtain the Nernst potential, reading delta V is equal to minus kBt divided by Z times E, log of the ratio of the inside concentration to the outside concentration. Now, to give just some typical numbers, the prefactor kBt divided by E at room temperature is 25 millivolt. And if we have a tenfold concentration ratio, we obtain a Nernst potential of 61 millivolt. Now let's look for this relation in cells and for the various ions. If we consider the sodium ions, where we have a low intracellular concentration and a high extracellular concentration, and apply the equation, we obtain a Nernst potential of 67 millivolt. Now, if we do the same for the potassium, where we have a high intracellular concentration and low extracellular concentration, we obtain a membrane potential of minus 83 millivolt. We also could look on anions, in particular chlorine. There again we find the intracellular concentration is low, the extracellular concentration is high, and we obtain a Nernst potential of minus 60 millivolt. So in total we see the Nernst potential is different for the different ions. Now if we go further in and measure the membrane potential by, for example, sticking in this thin needle into the cell and then just measure the voltage, we will see that cells, and that is very general, will have a membrane potential of minus 60 millivolt. So obviously something is missing in our description. And this is what we will now develop, finally leading to the Donnan equilibrium. So what we neglected so far is that in order to apply an equilibrium, these ions must be able to interchange between inside and outside through the membrane. Hence, the membrane has to be at least somewhat permeable to ions. Now, let's look on the permeability coefficients for different substances of the cell membrane. Now, starting, for example, with water, you see that the permeability of water is extremely high. It's in the order of 10 to the minus 2 centimeter per second. Now, high permeability we obtain for small uncharged or polar molecules. Now, larger, yet still unpolar charged molecules like glucose, the sugars, we will find typical permeabilities in the order of 10 to the minus 6 to 10 to the minus 8 centimeters per second. Yet charged substances, and in particular ions, are hardly permeable. The most permeable ion is the chlorine with permeability of 10 to the minus 10 centimeter per second. And then in a sequence, we have potassium and finally sodium, which has a permeability of 10 to the minus 12 centimeter per second. Hence, what we have to conclude here is that cell membranes are hardly permeable for ions. And in particular, there is also a sequence of ions where chlorine has the highest permeability, followed by potassium, followed by sodium. As of the permeability of the cell membrane, there will be a permanent flux of ions and other substances through the membrane in time. Be aware that even at equilibrium, there will be a flux, yet the net flux, so the number of particles going inside to outside, will not differ. Just to realize what those permeabilities mean, let's consider that there is a concentration difference, delta C, between the inside and the outside of a cell, and the cell is sitting in a bath, such that the concentration of ions on the outside is just constant. So with time, what you would expect is that the concentration of the inside and the outside should be equal, or the delta C should be 0. Now we can put forward a differential equation where we look on the change of the inside concentration as a function of time, and that is given by the concentration difference, delta C, times the permeability, PD, times the area of the cell divided by the volume of the cell. Now, this simple differential equation is solved by an exponential, where the concentration difference is fading out like an exponential e to the minus t divided by tau, where the typical time tau is given by the volume divided by the permeability and the area of the object. So let's calculate some of these timescales that are involved. And in our example, we will assume that the cell has a diameter of 6 micron. Now, if we take the values for water, we will find that the typical timescale to exchange the water content of a cell is in the order of 10 milliseconds. That means every 10 milliseconds, the complete water content of the cell will be exchanged. For potassium, this is very different. For potassium, we find that it will take 10 to the 8 seconds, which is in the order of 3 years, to exchange the potassium content of a cell. And likewise for sodium and for chlorine. So now the question is, how do those facts that we just discussed affect the equilibrium potential on the cell membrane? And that will lead us to the Donnan equilibrium. So first to wrap up, so we know cells contain charged molecules at a given concentration rho Q. Typically those are negatively charged, like DNA, like the sugars in the cell. Now, all those are highly impermeable, at least on the time scale of the lifetime of a cell. For ions, it's a little bit different. So ions like sodium, potassium, chloride are moderately permeable, although we saw that the time scales are very long. Now, in order to obtain the equilibrium condition, we actually have to take two equilibria into account. The first is the charge equilibrium. So neither inside nor outside the cell there should be a charge pileup. Cells are not positive or negative. And likewise, there must be also an electrical equilibrium given by the enhanced potentials. So first, let's look on the charge equilibrium. Well, for the outside, we have to state that the concentration of the potassium ions plus the concentration of the sodium ions minus the concentration of the chlorine ions have to be 0. Likewise for the cellar inside. Here the ions, potassium and sodium, minus the chloride concentration, minus the fixed charge given by the DNA, so rho Q, has to be 0. So those two conditions together define the charge equilibrium. Likewise, we have the electric equilibrium, meaning that the Nernst potential of the potassium ions has to be the same like the Nernst potential of the sodium ions and that of the chlorine ions, which by now fixes the ratios of the ions inside and outside of these three ions. This is called the Donnan equilibrium. Now let's use the Donnan equilibrium to kick out all the inside concentrations in charge equilibrium by replacing those with the Donnan equilibrium, which we define x, times the outside concentrations. Doing so, we now can calculate the value of x using the charge equilibrium that we required before. Now that leads to a second order equation in x, which we easily can solve. And let's use just Wolfram for doing that, and we get an equation for x. Now filling in the actual concentrations that we measure in cells, we find that x is 1.37, and that translates to a membrane potential in the Donnan equilibrium of minus 10 millivolt. Yet although we have now considered all the three ions together, the equilibrium potential that we obtain is by far off from that measured. Hence, we are missing an important ingredient, and we already can conclude that the membrane potential is not given by an equilibrium, but must be an out of equilibrium and controlled parameter.